Hey guys, today we're going to be starting chapter 25, which is, it's really electromagnetic induction. It's how electric fields and magnetic fields deal with each other, how they work together. We're not going to do all of chapter 25, just a little bit of it, because that's what's covered in the AP curriculum. So we're going to skip part of it. The part we're going to skip is electromagnetic waves, which is at the end. We will probably talk about some of that material later on in our modern unit. So electromagnetic induction was created, was discovered when Faraday did some experiments involving circuitry and magnetic fields. So it was known that a moving particle that was charged felt a magnetic force from a field. And what Faraday postulated was that a moving field could generate a current. And his postulate was formed after several experiments. He really just wanted to see what the effect of magnetic field on a circuit was. So he set up an experiment like the one replicated here. So he had a battery right there. Nice battery. You got a positive terminal, negative terminal. Charge flows around and goes through this solenoid. The solenoid creates a B field according to the right-hand rule. And the B field should interact with moving charge. So in this circuit down here, to start out with, there is no battery, there's no EMF or EMF to run the circuit. So it's just sitting there initially with its ammeter at 0. And right as soon as Faraday turned this top circuit on, connected it to the battery, closed this switch, a B field was created by this solenoid, and you can figure out using right-hand rule what that B field is. And what happened was in this bottom circuit, circuit 2, there was just a tiny little blip on the ammeter measuring the current. So a little tiny bit of current was generated for just a second, and then it stopped. So Faraday said there has to be some interaction here. Let's explore more to figure it out. To try to generate the current again, he used a bar magnet like the one shown here with a north end and a south end, north pole, south pole, and found that you could generate a current by either pushing the magnet into the coil or pulling the magnet out of the coil. Those would both cause a little bit of current to be generated. The same thing happened when you took a magnet, a horseshoe magnet like the one shown here, and moved the circuit in and out of the magnetic field. A momentary current was created that was going alternately one direction or the other. So what Faraday postulated and found experimental evidence for was that a current is generated if the magnetic field passing through the coil is changing. So as the field moves, it generates a force on those charges, which makes sense from a relativistic point of view. If the charges are moving through the B field, then the B field is moving relative to the charges, would also produce a force, which is inducing a current. And this type of current creation is called electromagnetic induction. It uses a moving B field to produce force on stationary charges. And this moving field generates an EMF, electromotive force. So when we were talking about circuits, we said batteries, looking like this, had an EMF that was equal to the change in voltage across the battery, and that is still true. That EMF in a battery is generated through internal chemical processes that we don't worry about, but they move the negative charge, or they move charge from the negative side to the positive side, giving it more voltage. So magnetic fields can also do this. They can move charges around internal to some system, which generates a potential difference and therefore an EMF. And we can use our previous knowledge to figure out how exactly this works, starting with the equation for one charge in a field, which is written down here. Force equals QVB. So So take a second here, look at this charge inside this conductor, this one positive charge right here, and convince yourself that this force shown here in the diagram is true. Using your right hand rule, you'll say velocity, your pointer finger is to the right. B field is going into the page, so that's the rest of your fingers. B field goes into the page, and force goes up. So as this bar, this conductor here, moves across the page to the right, all of its positive charges are going to feel a force going up. Similarly, all of its negative charges would feel a force going down because they experience the force opposite of the positive charge. So as that bar moves across, it's going to experience a separation of charge from a positive charge to a negative charge, which generates an internal electric field. So you're moving through a B field, which generates an electric field, and that's actually how light propagates, is generating those magnetic and electric fields. But this charge separation here generates the field, which is going to create a potential difference across the ends of the conductor. And this is going to continue to happen until there is an equilibrium, which means the forces are going to be balanced. So because that electric field is generated, every charge in the middle here is going to experience a force going upwards from the magnetic field, well, for the positive charges. And it's also going to experience a force that is attracted to all of these negative charges. And that force will be defined by the electric field in the region, which is Q times the electric field. So all of the charges will stop flowing once these two forces are balanced. And then that'll be as much field is generated and as much potential difference as will be generated, because everything will be at equilibrium, and it'll stay that way even as the bar continues to move through the field. If the bar stops moving through the field, all of these charges will go back to where they were, because the electric force will pull them back together, because this B field force will no longer be present, and the EMF will no longer be generated. The potential difference will no longer be there. So this equilibrium can only occur while this is moving. And the faster it's moving, the more EMF and the more charge separation there will be, because you have a larger magnetic force. Take a quick look at this question. It says a metal bar is moving through a magnetic field, and we're going to look and try to figure out what the induced charges on the bar are. So pause the video here, try to think it through using the right hand rule. I'm going to draw all of the charges on there and circle the correct answer, but pause it and you do it first. All right, so this one's actually a little bit tricky, and it's tricky because the B field and the velocity are in the same direction. And the force on a moving particle is Q V cross B, and if you know your cross products, you know that the cross product of two parallel things is 0. If you don't know your cross products, you could also say that Q VB sine alpha equals the force. And the angle between these two things, V and B, is 180 degrees. Sine of 180 degrees is 0. Therefore, this is 0. It's technically the 0 vector, but the force here is 0. So the charges will not be separated, and your answer will be E. On this field, however, the field and the velocity are perpendicular. So pause it again, try to figure out what the charges are going to do. All right, this one's going to have the positives on the left-hand side, the negatives on the right, which is answer choice B. You can use the right-hand rule to figure that out. All right, now we get to an example. It's going to take us a little bit to work through this example because there's a few equations we're going to have to resurrect from previous units. Question says a Boeing 747 aircraft with a wingspan of 65 meters is cruising at 260 meters per second over northern Canada, where the magnetic field of the Earth, with a magnitude of 5 × 10⁻⁵ Teslas, is directed straight down. What is the potential difference between the tips of the wings? So we're going to model this as a giant conductor. This is going to be my wings. I know that's not how wings actually look. With a wingspan of 65 meters, and it's going 260 meters per second. With my vantage point here, I'm going to say that the velocity is going to be coming out of the page. So the velocity is like this, and it's 200 meters per second. And the magnetic field of the Earth, the B field, is pointed straight down with a magnitude of 5 times 10 to the negative fifth Teslas. Awesome. So we're going to find the potential difference between the tips of the wings. First, let's figure out which way the positives are going to go and which way the negatives are going to go. You're going to have to use right-hand rule. So you point your pointer finger in the direction of velocity, which I'm going to say is out of the page. That's always the worst when the velocity is out of the page. It makes you hold your hand weird. And your B field is down. So that means here your force on positive charges goes to the right-hand side. So we'll go positive charges over here. And then negative charges will go opposite of that. And really they'll collect on the tips, not spread out like that. But for the sake of my drawing, we're going to leave it this way. All right, so we're trying to figure out the potential difference across the whole thing between this point and this point. So what we're going to have to do is figure out the electric field between those 2 points, just like you would with a capacitor almost. So let me go ahead and shrink this sucker down so I can have some room to work. Hopefully you can still see it. All right. So what we're going to do is start with the balanced force for a charge. So at equilibrium, after all the charges have settled out, the forces on each charge will be balanced. You'll have the magnetic force is going to the right, and the electric force is going to the left, and they cancel out to be 0. So we'll say that the force electric has to be equal to the magnetic force in magnitude. Now the electric force is Q times E, which is the electric field, and is equal to magnetic force, which is Q V cross B. Now you may notice that the Q's cancel out nicely, so I'm going to go ahead and take them out so I don't have to keep writing Q all of the time. We'll say electric field equals V cross B, which is equal to VB sine of alpha, the angle between them. The angle here between the velocity, which is horizontal, and the field, which is vertical, is 90. So we'll say that this equals velocity times the magnetic field. And we have both of those numbers. You have the electric field equals velocity V, 260, times B, which is 5 times 10 to the negative fifth, which ends up being something like 0.013 for your electric field. And then you have an equation somewhere that says that electric field equals change in potential over the separation, change in R, which would be delta V over D, basically. So we have the electric field there is 0.013, which equals potential difference over D. The distance between the 2 points we're looking at is 65 meters. So we'll do 0.013 times 65 to give delta V equals 0.845 volts. All right, which that process can lead us to a generalized equation like the one we see here. We'll do a quick derivation. We said that force electric had to equal force magnetic. So QE had to equal QV cross B. Cancel out the Q's. Field equals V cross B. And then we also said field was equal to big V. I'll put the little serifs on there for voltage. Big V for voltage divided by the distance across the things. So you could say that the voltage, which would be the induced EMF, change in potential equals the induced EMF, equals V cross B, which is VB sine alpha. We're going to assume we're at right angles. So we'll say V as in velocity times B times D, the distance across, which is also this L. So you could reduce that down to that the EMF equals the velocity times the field times the length of the object. So anytime you've got a conductor moving at a right angle to a field, this is the induced EMF. And you could use that as a voltage source for a circuit. Once you have done that to find the voltage source, or find the EMF of the voltage source for the current, you can use Ohm's law to find the induced current. So you'd say V equals IR, your V equals your EMF, current times resistance to find whatever current is induced in a circuit as the bar moves. So let's take a look at this circuit and use our physics know-how to determine what the magnetic field is like in this region. We've got an induced current flowing clockwise as this metal bar is pushed to the right. So if current flows clockwise, that means we have to go from high potential here, high V, to a low V, which means this will have the positive particles, this will have the negative particles. Now you try to use your right-hand rule and your physics know-how to figure out what direction the magnetic field is pointing. Pause the video, use your rules, try to figure it out. I'll answer it in just a second. All right, according to right-hand rule, where velocity, this arrow, is your pointer finger. Force, which is where your positive particles are being pushed, is your thumb going up. You get that the field has to be pointing into the page. Now, one might look at that and think, ooh, that sounds like infinite energy. You can just set the bar going through the field and everything's going to be hunky-dory. We're just going to have electricity forever, which is not how it works. Because we should know infinite energy is not going to be a thing. Anytime you get infinite energy, raise a red flag and say, somewhere I am wrong. So the reason that this is not perpetual motion, perpetual energy, is that the induced current that is felt in this bar is going to experience a force from that magnetic field, and you can convince yourself of this. You can say that the field's going into the page, point your right-hand rule field into the page, point your pointer finger in the direction of current going up, and you'll see that the bar experiences a force to the left because of its induced current. So, in order to keep that bar moving at a steady velocity to keep the current being induced, one has to pull that bar to the right to balance out that magnetic force to the left. So whatever thing is doing this pulling of the bar to keep it going at a constant velocity is doing work. And that work is equal to the force required to pull times the distance that it has pulled. So all of the energy change, all of the energy that's going into the circuit comes from this work of the hand or whatever is pulling this bar. And all of that power gets dissipated as, or dissipated through the resistance, probably a lot of it as heat, throughout the circuit. So the energy is put in by the hand or whatever's pulling, that's an input, and then it is dissipated by the circuit. And this is going to lead us to the power of a circuit, which we will derive in two different ways. So first up is going to be the circuit evaluation of power. We know that in circuits, power equals IV, which is also equal to I squared R. Yeah, because V equals IR. Now we had induced a current on the circuit. So say you've got circuit moving through a field. The induced current, we said, is equal to, or well, you could say IR equals the EMF. Therefore, induced current equals the EMF over R. So if you plug that in up here, where you do power equals E squared over R squared times R, you would get power equals EMF squared over R, because one of these powers of R is going to cancel. And we know from the previous discussion that EMF equals VBL, and you can plug that in here to get that power equals V squared B squared L squared over R, which is algebraically equivalent to this up here for power. Now this can also be derived using the hand pulling the bar on the circuit. So we said when the hand pulled the bar, the force magnetic on the bar, so I'm going to say on the bar because that's different than the magnetic force on the particles inside the bar. We're looking at the bar as a whole because of the current going through it. That is equal to the force of the hand. Now the force on a bar is the same as the force on a current carrying wire, which is equal to current times the length of the thing cross B, which we're going to say it's at a right angle, so it's just IL times B. Now that has to equal the force of the hand. Now the work of the hand equals the force times the distance. So that is ILB times the distance that it travels, okay? That is not the distance across the bar. That is the distance that the hand has pulled the bar. And this is work. So work is related to power. Power is work over delta T. So we're going to look at figuring out the power from this work. So the power from the hand equals this ILBD divided by delta T. Now, the thing to notice here is that the distance that the hand has moved divided by the time is equal to the velocity of the hand. So you'd say power equals ILB times velocity. And this is almost complete. All we got to do is figure out what that induced current is. And that induced current came in from up here. It is EMF over R. So we could say this equals EMF over R, LBV, and we also said EMF equals VBL. So to plug in VBL here for EMF, you would end up getting power equals L squared B squared V squared over R, which is precisely the same thing as we got. So the power of the hand is going into the circuit and coming out as the power of the circuit. So it's a nice conservation of energy kind of principle here. All right, so that's magnetic induction for you. You can apply this to circuits. It just generates the same kind of, it's a different kind of EMF, but EMF, which would be potential difference for a circuit, which is voltage of a circuit. So you can use the magnetic field to generate that EMF and then calculate things for a circuit, just as we had previously done. All right, thanks for watching. Tomorrow we'll be doing magnetic flux, Lenz's law, and Faraday's law. And then Thursday will be review. Friday will be your test. And then we'll have fall break for a bit. So please let me know if you got any questions. I should be pushing out a review by tomorrow, which is Wednesday. And there will be a little bit of homework over this in Google Classroom. All right, y'all have a great day. Let me know if you need anything.